Today we are going to read about electrostatics. So as the name suggests, electrostatics. Electro means an electron. It actually refers to an electron which is nothing but a charge. And statics means not in motion. So electrostatics is the study of charges, basically the study of interaction and effects of charges in static condition. So now, but what is meant by a charge? Charge. So charge is an inherent property It is an inherent property of a material due to its subatomic particles by which it interacts with the charge is an inherent property of a material which comes due to the subatomic particles, by which it gains the property of either attracting or repulsing a particle of similar kind. And till now we have heard that like charges repel and unlike charges attract. Now, what are these subatomic particles? It is due to proton, electron. So, the main difference is created by the electron. Now, here we say that like charges repel and unlike charges attract. So it means that there are two kinds of entities, out of which the kinds similar repel and the kinds different attract. So now what are the properties of charges? First one, of two kinds. Positive now positive charge and a positive charge repel, negative charge and a negative charge repel, positive, negative, attract. Now the previous statement meant this, like charges repel and unlike charges attract each other. The example for a positive charge is a proton and negative charge is electron. Right. Now the second property being charges are additive in nature, which means that suppose consider a body having five Coulomb of charge. Well, Coulomb is a unit, SI unit. So, suppose 5 Coulomb is the charge on a body, and someone additionally gives it 5 more. So, what we say is, here the body already has a positive charge of 5 Coulomb, and also it gains a positive charge of 5 Coulomb from somewhere else. So, the net charge will become now 5 plus 5, which is equal to 10 Coulomb. And suppose if it were negative charge of 5 Coulombs, so it would have become, so case 1, so here it would have become 5 plus, so the net charge now on the body would have been 0, and in case some other value, say minus 3 Coulomb, so it should have been 2 Coulombs of charge. So this way we say that the charges are additive in nature. We can add them, we can subtract them, the sign basically matters and nothing else than that. So next word. Now the third property is charges conserved, which means that can neither be created nor destroyed. Can only be transferred. So, say consider a body it has suppose 10 Coulomb of charge on it. Say I bring a rod here of negative charge. So now what will happen? Since this is negative charge, we know that the opposite charges attract each other. So because here we have a negative charge, more of the positive charge tries to come towards the rod. So we have an accumulation of positive charge here. Say we know that the charge present in this part is equal to 15 Coulomb. Now the question is, what is the charge in this part? So see, to this body, we haven't transferred any charge from anywhere. So the net charge will always be 10 Coulombs. So what will that mean? That this part, like 15 coulomb plus whatever, let the charge be q, is equal to 10. So charge will be equal to minus 5 coulomb. So the charge on this part would become minus 5 coulomb. Yeah. Now the fourth property, an additional statement can be added to the charges are conserved. Net charge on an isolated system remains the same. So here, for an example, let us take a body having 2 coulomb charge and a body having minus 10 coulomb charge. Now say I bring them in contact, and somehow I get to know that after a long time A has plus 4 coulomb of charge. So what amount of charge will B have? So here, see, we cannot say that this is a violation of the rule that charges are conserved. Initially it was 2 and now it becomes 4. Actually, this term plays a very important role. Isolated system. Since here it is in contact with some other system, we can't apply the thing that the net like initial charge will be equal to the final charge. But yes, considering this 2 particles as a system, we say that it still is isolated. So the net charge in this 2 bodies, the sum of the net charge in these 2 bodies will still be the same. So initially what was it? Initially it was 2 plus minus 10. Now finally it is 4 plus QB. Now this would mean minus 8 equal to 4 plus QB, which would mean QB is equal to minus 12 coulomb. So this is one more important point into the property of charges are conserved. Next, charge is quantized. So let it be any body. We say that the net charge on the body will be equal to, say net charge is equal to Q. Q will be equal to N times some charge, which should be the most basic charge. And it so happens that it turns out to be the charge of an electron. So charge on any body will be equal to N into E, where N belongs to the set of natural numbers. So we cannot have a body having charge 2 by 3 E, 4 by 5 E. These are all not accepted. Well, 2 E, 10 E, 10 power 27 E, these are all the charges accepted. So that is, the charge is quantized. The next property being charge is invariant in nature. That is, it does not depend on the frame of reference. Suppose we from a particular frame of reference we say that the charge on a particular body is 25 microcoulomb. So if you go to some other place, it will not happen that the charge becomes to something else, say 30 coulomb or some different number. It still remains the same. So this property basically tells that. Now let us see the basic difference between a mass and a charge. According to the properties, see the mass is also conserved. Mass is mass is not quantized. We don't know the fundamental unit of a mass by which we can say that it is equal to the n times that fundamental unit. So mass is not quantized. And though if it is quantized, we don't know the fundamental unit. Again, mass is invariant in nature. But what? See, mass, when considered two masses, they only attract. But two charges can attract or repel. So this is the very basic difference between the mass and the charge. Right. Now how do we charge a body? Like how do we get a charge onto a body? Suppose there is this body which I want to charge it by minus 100 microcoulomb. So what do I do? See, we know that the charge comes to a particular body from its subatomic particles, mainly electrons. Now each electron has a charge of minus 1.6 into 10 to the power of minus 19 coulombs, which we denote as E. Right? So, first of all, this body is getting a negative charge. So, this has more electrons than protons. So, we add a finite number of electrons to this body to get this charge. But what is the number of electrons we add to this body? That we can calculate from minus 100 microcoulomb is equal to, say n is the number of electrons we are adding here, minus 1.6 into 10 to the power of minus 19. From here we say that n is equals to 10 power 4 by 1.6 into 10 to the power of 19. So whatever is this number, if we add these number of electrons to this particular body, this body will gain the charge of minus 100 microcoulombs. So this is a way of charging the body. Now what if I want a charge of plus 100 coulomb? See, for getting a charge of minus 100 microcoulomb, what I did was add n electrons where n is equal to this much, so that I get a charge of minus 100 microcoulomb onto the body. Now what do I do to get a plus 100 microcoulomb? See, do I add protons? No, I would say no, because adding we cannot isolate protons. See, consider a nucleus having a proton, and there will be lots of electrons here, so it's very difficult to isolate a proton. Thus, instead of adding protons, see what does a neutral charge, what does neutral turn out to be? Plus and minus. So a positive charge and a negative charge would make this body a neutral. So to have excess of positive charge in it, I must remove this negative charge. So what I do here, I remove electrons to get positive charge. Now what is the number of electrons I remove? See, the calculation remains the same. For plus 100 I would remove the same number of electrons. So I would say, to get a charge of plus 100 microcoulomb, I would remove n number of electrons, where n is the same. So this way one can charge a body. There are even other ways too. Charging a body by induction. So see, consider there are two rods. Now we want to charge one of the rods with a positive charge. So let us get them into contact. Initially they are neutral in charge. Now see, what I do is, if I want this rod to be charged positively, I get another rod here of positive charge, so now since it is positive charge nearby this, so what it does is, it drags the negative charges here, and this surface would become excess in negative charge, and since the negative charge comes out here, this surface becomes positive in charge. Now, having the rod in the same way, near to this, what I do is, I separate the rods other ways. So this would still have those negative charge here, and this will have the positive charge. And now you remove the rod away from the scene, and since they are not in contact, it is still having an excess of negative charge, and it is having excess of positive charge, and they will retain the same. So finally we end up getting two bodies, one with a negative charge and the other with a positive charge. So this is another way of charging the bodies. Now let us see how two charges interact with each other. Let us first consider 2 point charges. Now, what is meant by a point charge? What is a point? We know that this is a point. But if I try to zoom in and see, this zoomed version would be this way, the solid. So here it may seem to be a point, but here it is not. So what does that mean? When do we consider a thing to be of point? When do we say a thing to be point? When its dimensions compared to the observable surroundings is negligible. Like say if I have a 10 meter long, 10 meter distance between two charges, and they are of radius 0.5 millimeter, then compared to this 10 meter, 0.5 millimeter is almost negligible. Thus, in this case, these bodies will be point charges. But consider the same bodies of 0.5 millimeter diameter, but having the distance between them as 1 millimeter. So here they are not point charges. It's similar to having like this big charge between the distance this much. So we have to be very careful while using these the concepts which we will be discussing right now for the point charges. We have to check whether it's a point charge or not in that system. So let's consider 2 point charges, Q1 and Q2. Now we know that these 2 charges will attract force on each other. Now the nature of force is, if both are alike, if both are of same sign, repulsive, if different sign, attractive. So we now read about Coulomb's force. Coulomb's force, according to this force is equal to force on 2 by 1. This force will be is proportional to basically the product of the 2 charges. Let's say the distance is r. This is proportional to the inverse of square of the distance between them. Thus we write that the force is equals to K times Q1 Q2 by r square, where K is a constant of proportionality constant. Now we know that force is a vector quantity, but we have given the magnitude of the force here. What will be its direction? Now when we are considering the force on Q2, we see that if Q1 and Q2 are both positive, then the force is repulsive. So the direction is this way. Outwards in the line joining the center of both the charges. So direction will be along center of both charges. Now we know this. Now what do we say? That force on 2 by 1 is equals to K times Q1 Q2 by r square. By Newton's third law, force on 1 by 2 will also be equal to K Q1 by r square. The only thing is, for both these both these forces, direction is opposite. So considering that both Q1 and Q2 are positive, I'll say if this is Q1, this is Q2, and this is the line joining the center, this would be F21 and this would be F12. So in simple terms, but remember the magnitude is still the same. The magnitude of force acting on both the particles will be the same. Now what is this proportionality constant? It turns out that this proportionality constant K is equals to 1 by 4 pi epsilon, where we know that pi is a constant and epsilon is the property of the medium. In which charges are placed. So if it is vacuum or air, we say that epsilon is equals to epsilon naught, and this is known as permittivity of free space. And its value is equal to (8.85 into 10 to the power of minus 12) Coulomb square by Newton meter square. Now if it is some other medium other than air, we say that epsilon is equals to epsilon r into epsilon naught, where this epsilon naught is the same as the permittivity of free space, and this epsilon r is called the dielectric constant of medium. So consider two charges in vacuum. The force will be equal to force of vacuum is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. And consider the same two charges in medium, in any medium. Say the force acting there is equals to dividing 1 by 2, we get so this gets cancelled, this gets cancelled, 4 pi epsilon, 4 pi epsilon, this turns out to be epsilon r. So we write an important formula here, that F vacuum by F medium is equals to epsilon r. The ratio of force exerted between the two bodies in vacuum to the force exerted between the same two bodies placed at the same distance in a medium is equal to the dielectric constant of that particular medium. Now it was okay when we had two charges. Now what if we have more number of charges, say Q1, Q2 and Q3. Now how do we find the force on, say, how do we find the force on Q3 in this particular arrangement? So here what do we know? See, let this distance be R13 and this distance be R23. So we know that the force due to 1 on 3 will be in this direction, and the force on 3 due to 1 and the force on 3 due to 2 will be in this direction, considering all are positive. So the force is repel, and we know that the force is a vector quantity, and so it we'll have to do a vector addition over here. So what do we say? The net force on 3 is equals to force on 3 due to 1 plus force on 3 due to 2. This is nothing but the principle of superposition. So what is principle of superposition? Principle of superposition is that the net force for principle of superposition for Coulombic forces is that the net force at a point is equal to the forces sum of the forces exerted by every other charge on the body. Just to mention, Coulomb forces are central in nature. Now what does this mean? When a force acts along the, let's say if this is a body and this is a body, this is the center, this is the center. The Coulomb force acts along this line. So whenever a force acts along the line joining the centers of the two bodies, that force is called central. So Coulomb forces are central in nature. Coming back to the point, we can find the force on a charge in a multi-charge system by using the principle of superposition. So now let us solve a few questions. See, there is this line. Over this, I place a charge of 4q here and a charge of minus q here. Consider this to be a point charges. Okay, well, let's remove the confusion. This is 4q charge and this is minus q charge. Now from and the distance here is d. At what distance should we keep a charge so that the entire system is in equilibrium? Now let us analyze this question in terms of regions. Let this be region 1, let this be region 2, let this be region 3. So see, if I have a charge in region 1, let it be positive. So if there is a charge in region 1, positive charge, due to this charge a force will act this direction, due to this charge a force will act in this direction. So it is possible to nullify the effect. Say in region 2, due to this charge a force will act in this direction, due to this charge also it will act in this direction. So there is no chance of nullifying the effect. And in charge region 3, due to this charge the force is in this direction, and due to this charge it is attractive, so this way again here we get a chance of nullifying the effect. So we cannot have a charge in region 2. Now let's suppose we have a charge of magnitude q in region 3. So let it be here. Let this distance be x. So what is the force on q? Force on q by 4q. This will be equal to k times 4q into q by d plus x square. Okay, and force on, magnitude of force. Here magnitude of force on q due to minus q is equals to magnitude of f q x square. Now since we are already considering the directions, for this net force on this charge to be 0, we say that k times 4q times q by x plus d square should be equal to k times q by x square, which means 4x square is equals to x plus d whole square, which would mean this would turn out to be 3x plus d times x minus d. Let's check. 3x square minus 3xd plus xd will give us minus 2xd. Okay, sorry, here it is minus, right? So this will turn out to be 3x plus d into x minus d is equal to 0, which means that x is equal to minus d by 3 or d. So see, if x is minus d by 3, which means that x is in this direction somewhere here, but we know that if x cannot be here, so we discard this answer and we say that at a distance from the negative charge at x equal to d. Now we erase all this. At a distance x equal to d, a charge can be present. Now what is that charge? See, now let us see on this thing. Let us evaluate on minus q. On this particular charge, since it is positive, we have considered it to be positive, the direction of force here is this way, and from this charge it is this way, right? And we know that this distance is d now. So what is the charge by q? Fq is equals to k times q into q, I am writing the magnitude here, by d square, and force by 4q is equals to k times 4q times q by d square. So for these to be equal in magnitude, q should be equal to 4q. But what if the force is equal to 4? Now consider that the answer which you got is true. Let us analyze the forces on this part. Here the force due to this is in this direction and the magnitude is k times 4q square by d square. Force due to this will be in this direction and will be equal to k times 4q square by it will be equal to 4q times 4q by 2d square. So this is equal to, see, this 4 and this 2 square gets cancelled, so k 4q square by d square. Now these are both equal in magnitude and opposite, so the net charge here is also 0, right? Thus the answer which you got is correct. It is very important in JEE to always analyze your answers. Whenever you get an answer, go back, put the answer in your question again and check it. So one conclusion which we draw is, at x equal to d, a charge of magnitude plus 4q can be present. Now the question is not yet over. Now we have analyzed this part. Now we erase off this x equal to d from negative charge. Okay, now the question comes like, can there be a charge present on the first part? Let us see. Now let us consider a charge over here, say q. Now and let the distance be x. Now if the net force on this charge is 0, what is the force by this charge on this particle? This is equal to, this is in direction this, and equal to k times 4q into q by x square, and the force by this is in this direction and equal to x plus d square. So for them to cancel, k times 4q q by x square should be equal to k times q by x plus d the whole square, which means 4x square plus 8xd plus 4d square should be equal to x square. 3x square plus 8xd plus 4d square is equal to 0. So the answer comes out to be x equal to minus 2d comma minus 2d by 3. So see, minus 2d by 3 would get us here, which cannot be the answer. Minus 2d would get us here, the answer which we got from this part. So what does this mean is, see, there is nothing that you have to know it earlier that from which part you have to proceed. Any part you take, you will get the same answer. So basically we have found out that the answer is only and only this. Only a positive charge of magnitude 4q can be put up at a distance of x equal to d from the negative charge, which is also x equal to 2d from positive charge. Because see, x equal to d would mean here or here, but x equal to d from negative and x equal to 2d from positive would lead us to only one position. Okay, so this is the way we solve a question. Now again, based on the same concept, this is the square of side A. I have 4 charges, positive charges Q present here, and a small charge Q at the center. Now what should be the magnitude of Q such that the net system is in equilibrium? So first of all, see, since it is at the center, the distances are all the same. So the charge at Q, due to this Q is this direction, this Q is in this direction, this Q is in this direction, and this Q is in this direction, all in same magnitude. So these both cancel each other, these both cancel each other. So whatever is the magnitude, we don't have to check the equilibrium at this particular point, because we know that it is already in equilibrium, the net force is 0. Now let us consider this particular charge. So this is the charge Q. By this charge, it will have a force in this direction of magnitude kq square by a square. See, k into q by the distance is a and its square. Force by this charge, it will be in this direction, again kq square by a square. Force by this small charge q will be in this direction, and it is 45 degrees since it is a square. Okay, and the magnitude will be let it be F1 plus F2, where F2 is a charge due to this. This will also exert a charge, exert a force on that. So now what is F1? F1 is equals to the charge by this part. First of all, if this is A, we know that this distance is A root 2 and this distance is A by root 2, right? So what is F1? F1 will be equal to K times Q by A by root 2 square, which is equals to 2K Q by A square. And what is F2? F2 was due to this particular charge. This would be equal to KQQ by A root 2 whole square, which is equal to KQQ by 2A square. So all in all, the net distribution will be upwards. We have KQ square by A square. Sorry, here we don't have Q. This is also a capital Q. Then we have here a charge of KQ square by A square. We have a charge here of KQ square by 2A square plus KQQ by A square. Now the net charge on the system should be 0. So net charge on this particular charge should also be 0. Now what is the so like the complete charges in horizontal direction and the charges in vertical direction should sum up to 0. This force component on this particular like horizontal axis will be KQ square by 2A square plus 2KQQ by A square times 1 by root 2 will be equal to minus KQ square by A square. Now why does this minus come? See, this is the component of this force in this axis. So the component of this force in this axis plus this force should be equal to 0. Now if I take this that way, it becomes minus KQ square by A square. So this A square and A square gets cancelled. K gets cancelled. 1Q gets cancelled. So we get Q by 2 plus 2Q is equal to minus root 2Q. From here we get 2Q is equals to minus of 2 root 2 q minus 1 minus q by 2. Take this that way and take the LCM. So finally we get the answer as so if this is the amount of charge placed here, we'll have the net system in equilibrium, because see, the same case lies here, the same case lies here, the same case lies here. So if this is at rest, all the other also will be at rest. So that is the answer. Now let us solve one more last question based on forces. Let this be a ceiling. See, this is a horizontal line, okay? And we are given that this particular particle has charge q and mass m. This also has charge q and mass m. Theta, gravity acts. Now the question is, find out the angle theta. And given that this distance is d. So, like, first of all, whenever we come across the question of force analysis, the first thing which we need to do is draw a free body diagram. Now consider this part, like this charge q. It has a tension acting over here. It has a gravity force mg, and it has a Coulombic force in this direction, which is equal to kq square by d square. Now if this is in equilibrium, what would I say? See, this angle is theta. I would say that t cos theta is equals to mg and t sin theta is equals to k q square by d square. See, t cos theta is equals to mg and t sin theta, the component along the horizontal direction, should be equal to k q square by d square. Now you divide both, you get tan theta is equals to k q square by d square mg. So theta is equal to tan inverse of okay. So this is the way we solve questions based on force analysis, free body diagrams, and charges. Now let us go to a concept of electric field. See, whenever there is a charge present, and there is another charge, we say that a force acts between them. But what actually happens is, even if this charge is not there, this charge creates its own influence in the space surrounding by in such a way that any charge placed at a point would face some sort of a force based on the influence of this charge, and that is what is called as field. Now importantly, field is a point parameter, that it depends on points. Say I go to a point at a distance r1 and the field is E1 over here, and I go to a place E2, R2, where the field is E2. So it may so happen that E1 and E2 are different, same or anything. The basic concept which I want to tell is, this is a point parameter, it depends on the point. Okay, but how do we know that there exists a field? See, to check a field, what we do is, initially we have a charge q, then we take a test charge and we place it at a point. If that test charge experiences a force in either this direction or this direction, then we know that there is a field present. Now what are the characteristics of a test charge? Test charge Q naught. It is very small, positive. Now what is the definition of electric field? Mathematically, we define electric field at a point P. Electric field is a vector, by the way, is equal to the force experienced by the test charge at the point P. See, electric field at a point P is defined as the force experienced by the test charge at the point P divided by the test charge, where the test charge tends to 0, like it's very small. This is the definition of an electric field. So, out of whatever we have learned today, let us go and try to find out the electric field of a few situations. There is this point charge Q. I want to find out an electric field exerted by this point charge. So what do? I go to a distance r and I place a test charge Q naught over here. Now what do I know? I know that the force is equals to, magnitude of force is equals to K Q naught by r square. So force by Q naught is equals to K Q by r square. So electric field, since this is the magnitude of electric field is equals to K Q by r square. Also the units of electric field are Coulomb per meter. So the electric field due to a point charge is equals to K Q by r square. At a point is equal to K Q by r square. And vector in vector notation, see what is the force here? It is into r cap, direction of r cap. So here also it becomes r cap. So electric field due to a point charge will be equal to K Q by r square into r cap. So this is all for today. In the next session we'll learn a bit more about electric fields, then finding out electric fields of continuous distributions, then Gauss law, and etc.